So this is the seventh session on on rigid body kinematics. Okay. So this is in continuation of the sixth session. So in this today we'll take up the second topic on rigid body kinematics, that is the velocity equation for a rotating rigid body. Okay. So first of all, I'll just outline what we are going to do in this video, what we are going to discuss. We know that when a rigid body rotates with respect to some given frame f, in general, at a given instant, two locations of this rotating body in general have different velocities. So our problem main will be that given a velocity of some location of this rotating body with respect to some given frame say f, and then we have to find the velocity of some other location of this rotating body with respect to the same frame. Okay, this is our topic of discussion in this video. Okay, so first I will before going to seventh video, you must definitely watch the first video on rigid body kinematics. Okay, only after seeing the first video on rigid body kinematics you should come to this one. Okay, so now first of all, so this is the suppose this is the given frame f. F is some given reference frame. Okay, M is some given rigid body. M is some given rigid body which rotates with respect to F. Okay, M rotates with respect to F. Okay, suppose the angular velocity of M with respect to F at a particular instant is vector omega. This omega is the angular velocity of M with respect to F. You assume that P1 and P2 are two locations of this M. P1 and P2 are two locations which are fixed in M. Either P1 and P2 are real or imaginary locations of M. So one more thing I would say, if you have any doubt about this real and imaginary location, you go to the seventh video on relative velocity. There you will get the detailed definition of reference frame. In that video, it has been explained in very great details what does this word mean, real and imaginary location. Okay, so there you can see in the seventh video on relative velocity you will get it. Okay, so P1 and P2 are two locations of M, real and imaginary locations of M. Vector from P1 to P2 is R. R is the vector from P1 to P2. Alright. Velocity of P1 with respect to F is say V1F at a given instant. And we have to find the velocity of P2 with respect to F at the same instant. As was discussed in the second video on rigid body kinematics, velocity of point P2 with respect to F, suppose I show it in this way, shown arbitrarily. So M is a body which rotates with respect to F. V1F is given, omega is given, R is given. We have to determine V2F. Now one more thing, since M rotates with respect to F, so in general V1F and V2F are not same, they are different. So as was discussed in the second video on rigid body kinematics, V2F and V1F are related via this equation. V2F is equal to V1F plus omega cross R. Okay, so this is the relation between V2F and V1F. So V2F is equal to V1F plus omega cross R. Alright. So V2F is equal to V1F plus omega cross R. So this is the relation between velocities of two locations of M, of a rigid body M which rotates with respect to frame F. Okay. So M rotates with respect to frame F, then and P1 and P2 are two locations of M, then V2F and V1F are related via this equation. So this is called the velocity equation for a rotating rigid body. This is called the velocity equation of a rotating rigid body. So this is the velocity equation for a rotating rigid body. Okay. So if we are given V1F, we are given omega, we are given R, then we can find V2F. Alright. One more thing should be noted. This equation is general relation. It is valid both for 2D and 3D rotation of M with respect to F. For both cases it is going to be valid. It is valid for both the cases. It is valid for 2D rotation, that is plane rotation, as well as 3D motion of M with respect to F. In both cases it is valid. This velocity equation is valid for both 2D and 3D rotation, 3D motion. It is valid for both 2D and 3D motion of M with respect to F. In both cases it is valid. Is it clear? What is plane motion? 2D motion, when I say 2D motion, it means plane rotation here. 2D motion means plane rotation. Or sometimes we call just plane rotation, we say as plane motion, okay? Plane rotation, okay, fine. It is valid both for 2D and 3D motion of M with respect to F. 2D motion means plane rotation, which will simply term in this case, this will call it as plane motion, okay? Plane motion. So this is a general equation, irrespective of whether M undergoes plane rotation or 3D rotation with respect to F. In both cases it is valid, okay? First what I'll do, I'll take up a problem on this concept, okay? So I'll take up a question. Question is this. Suppose a rigid body M moves with respect to ground. Denoted by G, and P1 and P2 are two material points of M. Also, coordinates of P1 and P2 are -1, 4, 3 and 3, -2, 4. They are both in meters. And angular velocity of M with respect to ground at given instant is 6i hat minus 2j hat plus 4k hat radian per second. This is the angular velocity of M with respect to ground at the given instant in IJK notation. Alright. So this I'll rub it now. Also, velocity of point P1 with respect to ground at the given instant is V1g, that is given to be 2i hat plus 4j hat plus k hat meter per second. We have to determine V2g at the given instant in IJK notation. Alright, fine. So V1g, I am told what is this. V1g is the velocity of P1 with respect to ground at the given instant in IJK notation. We have to find V2g. Alright. So this is general formula. Alright. So to find V2g, we will use that formula, velocity equation, which I mentioned just now. So V2g is equal to V1g plus omega cross r. Now we have to know omega cross r, and then we have to add to V1g. Now r is the vector from P1 to P2. So r is equal to position vector of P2 minus position vector of P1. Alright. So vector r is the position vector of P2 minus position vector of P1. So what is position vector of P2? Position vector of P2 will be 3i hat minus 2j hat plus 4k hat. Because if coordinates of point P are x, y, z, its position vector is xi plus yj plus zk hat. Alright. So position vector of P2 will be 3i hat minus 2j hat plus 4k hat minus position vector of P1. P1 is this minus I hat plus 4j hat plus 3k hat. 3 hat plus 2j hat plus 4k hat minus I hat plus 4j hat plus 3k hat. Minus plus becomes plus, so 4i hat on simplification. This is minus 4j minus 2j minus 6j hat. 4k minus 3k k hat. This is in meters, SI units, okay. So R is known. Now we have to add these two, we get V2G. Alright. So V2G, how to find V2G? That is the question. So V2G is equal to V1G. V1G is how much? 2i hat plus 4j hat plus k hat. 2i hat plus 4j hat plus k hat plus omega cross R. 4i hat minus 6j hat plus k hat. 2i hat plus 4i hat is 6i hat. 4j hat minus 6j hat minus 2j hat. K hat plus k hat 2k hat meter per second. This is therefore the required answer. Okay. So this was a practical application of this velocity equation for a rotating rigid body. As I mentioned just now, this formula is valid even in 2D rotation, plane rotation, as well as also for 3D rotation. In both cases it is going to be valid. Alright, fine. So these are a bit, alright. This was a bit, okay. Now, one thing I'd like to say, the formula which we derived just now, and we took that example also, V2G is equal to V1G plus omega cross R, or V2F is equal to V1F plus omega cross R. It is valid both for 2D as well as 3D rotation, both it is valid. We took a numerical on this case. See, in the numerical which we discussed just now, we found V2G by using that concept, alright, V2G. But then the calculation became relatively lengthy because we have to evaluate that cross product, na? Omega cross R in IJK notation. You have to use the determinant notation. That is time consuming, okay. Especially if you are interested in the plane rotation case, then also if you use this formula you will get the answer, but it becomes very time consuming, lengthy. Because we have to set up a coordinate system, write down the coordinates of those points P1 and P2, then find vector R, then again evaluate omega cross R using the determinant notation. That becomes lengthy, time taking. So our aim now is that if M undergoes plane rotation with respect to F, then we want to find the V2F in terms of V1F by easier method. We don't want to use that cross product notation because that takes a relatively long time to calculate. Okay. So our aim is to, for plane motion case, of m with respect to f, to convert this vector form of velocity equation into a scalar form. To convert the vector equation v2f is equal to v1f plus omega cross r into an equivalent scalar form. That is our aim. So that the evaluation of v2f becomes much more easier. Okay. So that evaluation of v2f becomes what? Much more easier. So that is our aim. So our aim is to convert this vector equation into an equivalent scalar form, so that the calculation time is minimized. Okay. We don't have to use that IJK notation, indeterminate notation, then solve. It becomes time taking. So into an equivalent scalar form, that is our aim. Alright. Before going to the scalar form, one thing I would like to say regarding circular motion, because that concept will be used just now. If a point moves in a circle with C as the center and R is the radius, R0 is the radius, P naught is the moving point moving in a circle. At certain instant of time, P0 is here, this is the radius of the circle. Suppose the circular motion, sense of circular motion is anti-clockwise. The angular speed of circular motion is omega naught. Then we know from the theory of circular motion kinematics of point that speed of point P0 is V0, that is equal to omega naught R0. This is the velocity of P0. Its direction is tangent to the circle at this point, corresponding to the sense of omega naught. The speed of P0 will be, velocity of P0 will be directed in this way, tangent to the circle. There is at right angles to this radius vector, and its speed is equal to omega naught R0. Okay, this is a result of circular motion which we will use just now. That's why I'm mentioning it. Okay. If point P0 moves in a clockwise circle, then V0 will be directed downward. Okay, fine. This result of circular motion should be kept in mind. Alright. So now our aim is to convert this vector equation into a scalar form. Okay. Our aim is to convert this vector equation into a scalar form. That is our aim. To convert this vector equation into corresponding what? Scalar form. That is the aim of our discussion, this video. Okay. So now I'll state the assumptions. This is the given frame F. M is a rigid body which undergoes plane rotation with respect to F. Suppose angular velocity of m with respect to f is omega at a certain instant. Suppose for the sake of argument, assume that the sense of omega is anti-clockwise. Okay. P1 and P2 are the two locations of m. P1 and P2 are the two locations of m. Locations of m meaning they are either real or imaginary locations of m. They are either real or imaginary locations of what? M. They are either the real or imaginary locations of m. Okay, fine. Suppose r is the vector from P1 to P2. Velocity of P1 is v1f with respect to f at time t. v2 velocity of P2 with respect to f is v2f at time t. Okay. Now we are assuming one more thing, that first that m undergoes plane motion with respect to f. M undergoes plane motion with respect to f. And one more thing, we are assuming that P1 and P2 are in the same base plane. Okay. Base plane I have explained in the first video of rigid body kinematics. I have explained what is that base plane. Okay. So one more thing, we'll assume that P1 and P2 are two locations of M, that is real or imaginary locations of M, and they are both in the same base plane. Are both in the same base plane. They are both in the what? Same base plane. Okay. So we know the vector form of the velocity equation that we already know. So V2F is equal to V1F plus omega cross R. Alright, fine. I'll rub this one. So see, suppose for the time being we assume that this is known. Omega is also known. R is also known. You have to find V2F, okay? Fine. So what do you see? V2F is the vector sum of these two terms. V2F is the vector sum of V1F and omega cross R. Alright. So if we have to find this V2F, then if we add these two terms, we get V2F. Fine. So what action we'll take? We'll take three actions. Okay. First action, action 1. See, our aim is to convert this into vector for scalar form, so that we don't have to calculate this omega cross R using that IJK notation, because that becomes time taking. Okay. So what is the first action? First action is this. We give a velocity of V1F to P2. See, it doesn't mean that P2 is moving in the velocity of P1. No. So that is when we are meaning that if you evaluate these two terms, resultant of these two terms, we get V2F. First action is this. Point P2 is assumed to move with a velocity of V1F. Or we'll say otherwise, give a velocity V1F to P2. Okay, so I'll write it here, first action. Point P2 is assumed to move with velocity of P1. That is, we give a velocity V1F to P2. We give a velocity of V1F to P2. We give a velocity of how much? V1F to what? P2. That is the first action. Fine. Now second action. Action 2. Second action we have to discuss. Okay. Now what is second action? Second action is the evaluation of this term, omega cross R, without using that IJK notation. Evaluation of the term omega cross R without using the IJK notation concept. Okay. That we have to evaluate. Fine. So now, first of all, how do you evaluate this omega cross R? Okay, fine. Without using that determinant notation. See, we can evaluate this term much more easier way. First of all, we must know what is the concept of relative velocity between 2 points in a given frame F. It was completely discussed in great details in the chapter on video on relative velocities. Okay, you'll get it there. If you go to the videos of relative velocity, you'll get it there. Okay. So we know from the theory of relative velocity between two moving points that relative velocity of P2 with respect to P1 in frame F is just equal to V2F minus V1F. Okay. Now when P1 and P2 are two locations of M, in that case we also know from velocity equation that V2F is equal to V1F plus omega cross R. So in comparing these two terms, from this equation we see that V2F minus V1F is just omega cross R. So from these two equations, it is seen that this and this, they are V2F minus V1F, they are both same. So these two should also be same. So it is seen that Vp2P1F is just equal to omega cross R. Okay. So Vp2P1F is just equal to what? Omega cross R. Fine. So this I'll rub it. So Vp to P1f is equal to omega cross R. Fine. So from if we substitute this term by this, what will we get? We'll get this. V2f is equal to V1f plus Vp to P1 slash f. This quantity denotes omega cross R. So Vp to P1 slash f is just the term omega cross R. So velocity of P2 is the vector sum of this and this. First section we already taken. Fine. Alright. Now to evaluate this term. Now see, one more thing I would like to say. One more thing I would like to say now. See, suppose a point moves in a circle with center at C. Suppose a point P moves in a circle with center at C and radius say R0. Alright, fine. Then this distance is Cp is fixed, R0 constant. P and C are confined to lie in the same plane of circle. They are in the plane of circle. And C is fixed. C is fixed. So if P moves in a circle with center at C and radius R0, then C is fixed. Distance between C and P is constant, R0 radius. And P and C are always confined to lie in the plane of circle. Okay. Conversely, if C is fixed and P and C are always confined to lie in the same plane, C is fixed and P and C are always confined to lie in the same plane, and distance between C and P is constant. This implies that P moves in a circle. Okay. So if C is fixed and distance Cp is constant and C and P always lie in the same plane, implies that P moves in a circle with center at C. P moves in a circle center at C. Okay, so I'll repeat it. If point C is fixed, distance between P and C, moving point P and C is constant, and P and C are always confined to lie in the same plane, then P moves in a circle with center at C. Okay, and speed of P due to circular motion will be omega R0. Fine. And direction omega R0 will be tangential to the circle at P, corresponding to the sense of angular speed omega. Fine. I'll rub this one. Fine. So see, so this concept will apply here. Okay, this is the frame F, this is M, this is P1, P2, this is R vector, omega, this is V1F, this V2F. So now see, Now we already know that velocity of P2 with respect to P1 in frame F is just equal to omega cross R. Fine. Alright. So now see, instead of C we take P1 and instead of P we take P2. Instead of C we take what? P1 and instead of P we take what? P2. Fine. Alright. Now see, first of all, velocity of P2 with respect to P1 in frame F is omega cross R, which is a non-zero term. This is a non-zero term. Why? Because if we evaluate the magnitude of this term, how much will be the magnitude? Cross square rule, magnitude of omega into magnitude of vector R, that is R. Now what is the angle between omega and R? P1 and P2 are in the same base plane, so vector R lies in the base plane. And in plane motion, we know that vector omega is normal to the base plane. Direction of omega is perpendicular to the base plane. That is, direction of omega is perpendicular to vector R. So angle between omega and R are 90 degree. So omega cross R magnitude will be omega into R into sine 90 degree, which is, this becomes 1. So this becomes omega R, which is non-zero. So now see, we apply this concept here. Instead of C we take P1 and instead of P we take P2. Now see, with respect to P1, P1 is fixed, definitely with respect to itself. P1 is what? Fixed. And distance P1, P2 is equal to R, constant. Why constant? Constant because P1 and P2 are the two locations of rigid body M. And it's the property of rigid body that the distance between any two locations of this rigid body is constant. So P1, P2 is R, that is constant. And P1 and P2 are in the same base plane by assumption. P1 and P2 are in the same base plane. So with respect to P1, P1 is fixed. Distance P1, P2 is constant because they are the two locations of rigid body M. And P1 and P2 are in the same base plane by assumption. And Vp2 P1F is non-zero. That is just equal to omega R. So this means, if we apply this concept here, this concept which we discuss here, this we apply here. This means P2 moves in a circle. P2 moves in a circle with respect to P1. Okay, whose center is at P1. Whose center is at where? P1. And radius is how much? R. And what is the angular speed of this circular motion? It is same as the angular speed of M with respect to F, which is omega. This are a bit. So we reach at the conclusion that with respect to P1, P2 moves in a circle whose center is at P1 and radius is R, and whose omega is same as angular velocity of M with respect to F. So this means that Vp2 P1F has the magnitude of omega R, as I stated just now. This term is just omega R. Okay. So see, magnitude of Vp2 P1 omega cross R has been found directly. Omega into R into sine 90 degree, that is omega R. So we don't have to use this notation at all. IJK notation is not to be used. So in much more easier method we evaluated this term. Okay. So now two possible cases arise. Omega of M with respect to F may be in anti-clockwise sense or in clockwise sense. Here we assume anti-clockwise sense. Alright. So two cases. Sense of omega is say anti-clockwise sense. So now what we'll say? With respect to P1, P2 moves in anti-clockwise circle whose center is at P1 and radius R. So with respect to P1, P2 moves in anti-clockwise circle. Okay, and this is common here, and whose center is at P1 and radius R. So what action will take? This action will draw here. This is P1, this is P2, this is radius R. Omega of sense of omega is anti-clockwise. So with respect to P1, P2 moves in anti-clockwise circle whose center is at P1 and radius R. So in this, what action, what speed will give to P2? Omega R. Right angles to this radius. One thing, okay? And second, if omega of m with respect to f is clockwise, in this case what will give? So in this anti-clockwise case, second action what will do? Will give a velocity of omega r to P2, normal to line P1, P2, corresponding to anti-clockwise sense of omega. Fine. And what about this omega clockwise? We give a speed omega r to what? P2, and perpendicular to P1, P2, such that sense of omega is clockwise. So such that sense of omega is clockwise. So how will you show this term here? This is P1, this is P2, this is R. So in this case we'll say P2 moves in a clockwise circle with center at P1 and radius R. So what speed will give to P2? Omega R. Omega R, direction omega R will normal to P1, P2, corresponding to sense of clockwise omega. This is the second action. Fine. Alright. This I'll rub it all right. So, what is the second action which we are going to take? Second action will be, we give a speed omega r to P2 at right angles to P1, P2, corresponding to the sense of omega of m with respect to f. Corresponding to a sense of omega of m with respect to what? F. So, in action 2, what we have to take? Give, if sense of omega is anti-clockwise, in that case, give a speed omega r to P2 and perpendicular to P1, P2. Give a speed omega r to P2 and perpendicular to P1, P2, such that it corresponds to clockwise omega. If omega is clockwise, sorry, this is anti-clockwise, sorry. Okay. If sense of omega is clockwise, in this we give a speed of omega r to P2 and perpendicular to P1, P2, such that it corresponds to clockwise omega. Corresponds to clockwise omega. Okay, so this is second action. So see, in this method, second action, in this concept, scalar concept method, we don't have to use that IJK notation of determinant notation to evaluate that omega cross r, IJK notation that that is not needed now. Directly we can get. Okay, the second action is obtained. And what is going to be the third action? Third action is simply, we add the two velocities given to P2 in the first two steps vectorially to get the velocity of P2. That's all. So vectorially add V1F and omega cross R to get V2F. That's all. So three-step procedure. Fine. The third action what we have to take? Vectorially add V1F and omega cross R to get V2F. Vectorially add V1F and omega cross R to get what? V2F. So this is a three-step procedure. Fine. So in this video I discuss this basic theory, but this is not complete. In the 8th video I'll continue in this. So if you go to the 8th video, no, you must first see the 7th video, then you must go to the 8th video. If you directly go to 8th video, then you will not understand it. Okay, so this I'll close it here. Now I'll continue with the 8th video, I'll continue with the theory in the next 8th video. Okay, so I close it here.